So here in Chapter 7, we're going to start exploring how atoms and molecules react. Now, atoms and molecules are so tiny that chemists are seldom able to deal with them one at a time. When we weigh even a very small quantity of a compound, huge numbers of formula units, perhaps 10 to the 19, are present. The formula unit may be atoms, molecules, or ions. So to overcome this problem, chemists long ago defined a unit called the mole. All right, so what we're going to do here is we're going to look at this unit called the mole and how it relates to something called Avogadro's number. We can find similar counting terms in our everyday life. For example, a dozen means 12 of something, 24 cans is often referred to as a case, a gross is 144 units, and a ream is typically 500 sheets of paper. So a mole is the amount of substance that contains as many atoms, molecules, or ions as there are atoms in exactly 12 grams of carbon-12. The important point here is that whether we are dealing with a mole of iron atoms, a mole of methane molecules, or a mole of sodium ions, a mole always contains the same number of formula units. The number of formula units in a mole is called Avogadro's number. Now, what I mean by a formula unit, for example, is what we discussed on the previous slide. So, a case equals 12 units. Again, the number of formula units in a mole is called Avogadro's number. It is named after the Italian physicist Amedeo Avogadro, who first proposed the concept of a mole but was not able to experimentally determine the number of units it represented. So here, 1 mole equals 6.02 times 10 to the 23 items. So 1 mole of an element equals 6.02 times 10 to the 23 atoms of that element. 1 mole of carbon equals 6.02 times 10 to the 23 atoms of carbon. 1 mole of sodium equals 6.02 times 10 to the 23 atoms of sodium. So just to emphasize this again, we call 6.02 times 10 to the 23 of anything 1 mole. All right, so here if we look at table 7.1, we can see that 1 mole of aluminum contains 6.02 times 10 to the 23 atoms of aluminum. Let's just look here. 1 mole of water, which is H2O, contains 6.02 times 10 to the 23 molecules of water. Okay, so again, keep this in mind. 1 mole always equals 6.02 times 10 to the 23 of something. So we can use this as a conversion factor. And you can see the relationship here. We can either have 1 mole in the numerator and Avogadro's number in the denominator, or Avogadro's number in the numerator and 1 mole in the denominator. It just depends upon the problem at hand. So let's look at how to convert moles to molecules. Avogadro's number is used to convert moles of a substance to the number of particles of that substance. So the question asks, how many CO2 molecules are in half a mole of CO2? So we're given half a mole, we need to find out how many molecules this is, and we know our conversion factor. So we can say that 1 mole of carbon dioxide is 6.02 times 10 to the 23 molecules of carbon dioxide, and 6.02 times 10 to the 23 molecules of carbon dioxide is to 1 mole. And then you can set up the calculation so that, again, usually what I've said to you with all of these problems is you put that given value first. Not always, but usually that given value that only has the 1 unit comes first. And then we use our conversion factors. And always in the last conversion factor, you want to have the unit that is desired in the numerator. So your moles of carbon dioxide cancel out, and we are left with 3.01 times 10 to the 23 molecules of carbon dioxide. All right, so let's do a learning check. What is the number of atoms in 2 moles of aluminum? All right, so pause your video and answer the following question. All right, so I wrote down what is given. I wrote down my conversion factor. I can see moles cancel, And the final answer should be C, 1.2 times 10 to the 24 atoms of aluminum. So it's 2 times 6.02 times 10 to the 23. So this just lays out the problem how I did. All right, so there's your conversion factor. And then finally our moles cancel, and you see that it's 1.2 times 10 to the 24. I want to take note that there's two significant figures because we have two significant figures here in our given quantity. All right, here's another learning check. What is the number of moles of sulfur in 1.8 times 10 to the 24 atoms of sulfur? Pause your video and determine the answer. So what you'll see, this time I just oriented my conversion factor with my desired unit in the numerator. My atoms of sulfur cancel, and then I am left with 3 moles of sulfur atoms. So again, this is just showing you how you set up the calculation, our conversion factors, and then we cancel and we get 3 moles of sulfur. Again, two significant figures because there were two significant figures in our given quantity. Now what we're going to do is we're going to look at the moles of elements when we have a chemical formula. So listed here is the chemical formula for aspirin. And what you can see in expanded form that there are 9 carbons, 8 hydrogens, and 4 oxygens present. The subscripts in a chemical formula show the relationship of atoms in the formula. The moles of each element in 1 mole of a compound. So, in 1 molecule of aspirin, we have 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. In 1 mole of aspirin, there are 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. We can use this relationship here to write new conversion factors. So here are the conversion factors. For aspirin, if you have 9 moles of carbon per 1 mole of aspirin, we can have 8 moles of hydrogen per 1 mole of aspirin and 4 moles of oxygen per 1 mole of aspirin. Or you can invert those conversion factors depending upon the problem at hand. So let's do a learning check. How many atoms of oxygen are in 0.15 moles of aspirin? All right, so this problem requires 2 conversion factors. We are given that we have 0.150 moles of aspirin. The question we need to answer is the number of oxygen atoms in that 0.15 moles of aspirin. So we need to have the conversion factor that there are 4 moles of oxygen per 1 mole of aspirin, and then that there are 6.02 times 10 to the 23 atoms per 1 mole of oxygen. Again, we always want to end with the desired unit in the numerator. So let me write out the calculation. I'm putting 0.15 moles of aspirin as my first number. Now again, typically you'll start with what's given. Then I can use my 4 moles of oxygen per 1 mole of aspirin. And then finally, my last conversion factor, 6.02 times 10 to the 23 atoms per 1 mole of oxygen. And now I'll cancel my units. My moles of aspirin cancel, my moles of oxygen cancel, and I'm left with atoms of oxygen in the numerator. So my final answer is 3.6 times 10 to the 23 atoms of oxygen. I only need that should be 3.61. I need to have 3 significant figures here because I have 3 significant figures in my problem. So this is just stepping you through the calculation and writing down what's given and what you need to find. Here are the conversion factors that are needed. And then there is the calculation set up, and you can see 3.61 times 10 to the 23 atoms. We're going to use this concept of the mole throughout this chapter. So if you're struggling with this, please make sure you do some problems and reach out to me.